we've looked at pressure and we've looked at density. I want to look at liquids in particular now. So the first thing that we want to do with a liquid is consider the volume. The big difference between a liquid and a gas really is that a liquid has a set volume where a gas doesn't. So what that means, if I have a cup full of water, like this, and I have maybe 200 milliliters of water. If I pour that into a bowl, so I'm going to pour this in here, I'm going to still have 200 milliliters of water. What's different is that the area of the cup here, if I take like a cross-sectional area, is relatively small, where over here my cross-sectional area is considerably larger. So if that's area 1 and this is area 2, I can get some kind of a relation between these. Now this is a little bit tricky because I don't have these very regular shapes, so let's look a little bit differently. Let's stick with just cylinders. Maybe I have a big cylinder like this, and over here I have maybe I have a cylinder like this, and I put some kind of a liquid in here, and I can feed this to the side. Now over here, maybe I have a really big cylinder. I can do this. I can use this to actually do a pretty cool thing. Maybe on this side I have a big block, and this thing's going to have a very large mass. Let's go 1,000 kilograms. So a metric ton of mass. And I'm going to give this thing an area of maybe, let's go 4 square meters. Over here I'm going to give this thing an area. If this thing has a radius of 10 centimeters, that would be 0.1 meters. Squared is 0.01 times pi is something like 0.03 square meters, and that's a 10 centimeter radius. Let's go a little bit smaller. Let's give this thing an area of 0.01 square meters. So this side I'm going to call side 1. This side I'm going to call side 2. And what I get with this conservation of volume, if I want to push this side down by a certain amount, like let's say to here, I have a volume of liquid in here, and that volume is going to be equal to area 1 times h1, where h1 is however far I push this thing down. Well, what that's going to do is take this thing and push it up by the same volume. If this piston moves down, the water that's in here, I just decided it's water, the water that's in here has to go somewhere. So it pushes through this way and has to push up. And that's a direct consequence of having a constant volume. The volume, we can't just compress it and make it take up less space. This has to go somewhere. So then this whole thing over here is going to move up by a certain amount. The amount that that moves up by is right here. The same amount of water that I had on the left side, that I pushed away on the left side, had to go up over here on the right side. So there's going to be some amount of height here, but because this one was really narrow and this one is really wide, if I take my narrow thing and pour it into something wide, it's going to take up less height. If I take my narrow column of water and displace it over here, it's going to displace not by as much height just because that area is so much bigger. So over here, I had volume 1 is area 1 times h1. Over here, I'm going to say volume 2 is area 2 times h2. And these volumes have to be equal to each other. So area 1 times h1 has to be equal to area 2 times h2. This is a conservation of volume equation. And one thing that you'll find is that with fluids you get a lot of equations that are really straightforward like this, or really simple at least. So then I gave the example of putting a big heavy mass over here, and there's got to be a reason for doing that. On the left side, I am applying a force to do this. On the right side, I am going to get a force. And there's a relation there too. The pressure that I'm putting on the left side is going to be equal to that force, F1, divided by area 1. That's what pressure is. The pressure that I get on the right side is going to be equal to F2 over area 2. Now, if this liquid is not compressible, and it's not, then the force isn't going to match necessarily, but the pressure does have to be consistent. Which means the pressure on the left has to be equal to the pressure on the right. Now looking at what that is, that means F1 over A1 is going to have to be equal to F2 over A2. Here's where it gets interesting. Area 2 is a lot bigger than area 1, which means I'm dividing by a big number over here. I'm dividing by a small number over here. If these two are going to be equal to each other, then I get a big force on the right to balance a small force on the left. Let's look at what it is with these numbers. Over here, the right side, I have the force needed to lift this thing is going to be 1,000 kilograms times 10 meters per second squared equals 10,000 newtons. That's a lot of force. The area is 4 square meters. So the right side of this thing is 2,500 newtons per square meter. The left side, I don't know what my force is, but I do know that my area is 0.01 square meters. So if I try and do this equation, I'm going to get that F1 over 0.01 square meters equals the right side, 10,000 newtons over 4 square meters, or 2,500 newtons per square meter. If I'm solving for F1, I multiply by 0.01 and I get 25 newtons. 25 newtons is the weight of a 2.5 kilogram block. So think 5-6 pounds, something like that. You have a 5 or 6 pound block on the left side, the weight of a 5 or 6 pound block on the left side, and you can lift a metric ton on the right side. This is something that we do with hydraulic lifts and jacks, things like that. On the right side, maybe we want to lift a car, but we don't want to lift a car worth of force. So instead, we make some kind of a hydraulic connection like this, and we say, you know what, let's have a small area over here on the left, a small area piston on the left. We can push down on that with a small amount of force, and because of the ratio of the areas, we're going to amplify that force a lot on the right side. It means that we get this second equation that says F1 over A1 equals F2 over A2. This one's a conservation of pressure. So a very, very similar equation. But it does leave the question of, why can I get away with this? Doesn't it seem like if I can just amplify force like this that I'm getting something for nothing? Almost. On the left side, I'm applying a force of F1, and I'm doing that over a distance of H1. Force times a distance, this looks a lot like work, which is an energy input. On the right side, what I'm getting out is an F2, and I'm getting that over a distance of H2. This is my energy output. But because H2 is so small and F2 is so big, F1 is small, H1 has to be really big. The other way to say that is to say, because of conservation of volume, if I've got a big area over here and a small area over here, I better have a big height on the left side. So I get the same amount of energy out as I put in, minus frictional effects, but we're not going to worry about that right now. I get the same amount of energy out as I put in, but to do that, I'm going to need a really big distance on the left. So if I want to raise this car, yes, I can do it with 25 newtons on the left, but if I want to raise this car by 10 centimeters, I'm going to have to drop this thing by a long way. It's a factor of, 10, 100, 400? It's a factor of 400 on area. Area 2 over area 1 is 400, which means H1 over H2 is going to be 400. If I want to lift this car by 10 centimeters on the left side, or on the right side, 10 times 400 is 4,000. That's 40 meters. I will have to depress this side by 40 meters. So a lot of times these like curl and things like that, or we won't have as big of an area ratio, or we have ways, like with a hydraulic jack, of kind of locking in. Every time you pump this, you might only pump this a small distance, and then it lifts a little here. Pump a small distance, and it lifts a little here, which is why you have that handle on the left side of a jack. You can just kind of keep pumping the handle, and that'll keep lifting this. You don't get away with one pump to lift the car as far as you want it to lift. That's the idea of volume, conservation of volume, and conservation of pressure with an example worked out. So that's what I've got.